Today, our topic is on global noise challenge and slag potential. As we know, noise pollution today is a huge problem everywhere. It's a it's a sort of a public health hazard. If you go through the few statistics like Europe, 22% of the population endures traffic noise beyond 65 decibel. And in US, this translate to over around 30 billion US dollar in lost productivity and healthcare cost. Meanwhile, the steel industry is producing up to 300 million tons of slag annually, with barely 35% utilization in developed countries. This convergence of challenges opens the door to a breakthrough using slag's unique architecture to control noise while reducing environmental impact. Scientific fundamental of slag acoustic is a burning topic in today's world, and its understanding always helps in mitigating the projects related in this field. Slag's ability to absorb sound stems from three key mechanisms. The first, viscous air damping, where sound waves lose energy as they bounce through interconnected pores, perfect for mid to high frequencies. Second, thermal conduction at pore walls, which dissipate acoustic energy as heat. And third, resonance trapping, where spatially shaped pores trigger uh, the resonance crucial for low frequency noise control below 500 Hz. Now coming to the slide which shows a structural property relationship, and it's very important. To engineer optimal slag acoustics, we focus on five core property: porosity, pore size distribution, uh, uh, tortuosity, bulk density, and flow resistivity. High porosity between 40 to 80% boosts absorption. Multimodal pore sizes respond across diverse frequencies. Tortuosity elongates wave path, while flow resistivity in the range of 10 to the power 4 to 10 to the power 6 PAS per meter square govern damping efficiency. These structural traits turn slag from waste into performance grade acoustic material. A porous ceramic system. This is also a very important thing that is to be known by user segments. Recent breakthrough have turned steel slag into high function ceramic. For instance, mullite whisker reinforced ceramics crafted from construction waste and additive achieve sound absorption coefficient above zero point 0.8 at mid-high frequencies, and flexural strength of 23.7 MPa. Meanwhile, silica carbide modified closed pore structure enhance absorption by nearly 70% in the low frequency range, while reducing sound transmission by up to 7 decibel. These ceramics combine strength and silence. Coming to the advanced slag material innovation, slag is not a one size fit all material. Its versatility shines in various innovation from lightweight geopolymer composites to previous concretes. A matrix of GGBS and vermiculite with coir fiber achieves low thermal conductivity and dual acoustic thermal performance. Lightweight geopolymer concrete using LECA boost mid-frequency absorption by 56%, which is a good value, and tomography confirm pore connectivity in previous concrete ensure both sound reduction and water infiltration. Each system serves a tailored function. Metamaterial concepts. Now coming to the titanium slag is paving the way for acoustic metamaterials. With layered porous structures, these materials disrupt stress waves using contrast in elastic modulus, reducing wave intensity up to more than 67%, almost 70%. Such design enable blast resistance infrastructure and noise protection in high impact zones. The innovation lies not just in what slag is, but in how its geometry transforms sound behavior. Now coming to the performance analysis, global case study, or we can say globally slag acoustics are proving their worth. In Spain, slag coal ash barriers achieve 7.2 decibel roadside noise reduction at 40% lower cost than fiberglass. In building, slag-based geopolymer walls boosted NRC from 0.31 to 0.65 with added thermal efficiency. Industrial enclosures made of slag ceramics reduced compressor noise by 11.3 decibel even under 180 degrees centigrade operating condition. These results underscore a real world viability. Coming to the field implementation results. Implementation strategy vary by environment. Precast acoustic panel made with 80% slag and centered at 1150 degrees centigrade are modular solution for tunnels. In situ, applications like slag previous concrete offer stormwater management and 8.2 decibel traffic noise reduction. Even mortar like vermiculite slag plasters deliver SAC of 0.75 at 500 Hz with excellent thermal resistance. Slag is finding its place in building, roads, and machines. As for design optimization methodologies is concerned, engineering slag acoustic start with gradation control. Slag particle size between 4 to 8 mm yield the highest absorption due to optimized surface to volume ratio. Whether you are designing for infrastructure or indoor use, tuning aggregate size is key for frequency targeting and performance consistency. Now let us have a look on pore structure engineering, which is a very vital aspect. Pore architecture is a science in itself. Using X-ray tomography, designers can visualize and optimize pore connectivity, achieving ideal flow resistivity for targeted applications. Foaming techniques using silica carbide create tunable pore distributions while controlling sintering in nitrogen atmospheres prevent pore collapse. These processes make slag material acoustically responsive and structurally reliable. Now coming to the implementation framework and sustainability impact. We can say that scalable deployment options include precast panel, previous concrete and acoustic plasters. ACBFS based concrete not only reduces traffic noise by over 8 decibel but also infiltrates stormwater, combining two infrastructure needs. With slag mortar and modular wall system, we are seeing acoustic design merge seamlessly with circular construction. Now coming to the economic impact, slag acoustics are economically compelling. They lower raw material cost by 60 to 80% is a good value. On lead credits for recycled content and regional sourcing and align with circular economy goals. Each 100 meter square acoustic system can valorize 8 to 12 tons of slag and is 100% recyclable. That's cost saving and carbon reduction in one package, and thus it is so attractive. Now coming to the challenges and future research frontiers. Yet challenges persist in these, like slag composition variability especially in CaO and FeO can impact acoustic behavior very severely. AI driven blending and real time composition monitoring are tackling these issues. Long term performance threats like carbonation and iron leaching are being addressed through nano coating that preserve up to 95% of pore structure after aging test. We are overcoming technical hurdles with a smart science. Now coming to the emerging research frontier, the frontier is exciting, from micro resonators in EF slag to bio-inspired 3D printed lattices and nanoporous gels. Multifunctional systems now incorporate PCM for thermal buffering and TiO2 coating for air purification. AI and IoT together are creating responsive acoustic system that adapt in real time. Slag is entering the digital age. Now coming to the conclusion and implementation roadmap, Slag's natural multiphase composition gives it unparalleled wave dissipation abilities with geopolymers for building, ceramics for industry and previous concrete for infrastructure. We have built a triad of solutions. Each ton of slag used avoid 1.2 ton of CO2, saves 3.4 meter cube of landfill space and cuts 5.7 gigajoule of production energy. This is more than innovation, it's sustainability in action.